Yeah, so welcome student, welcome to this class, and our course is MA425 Topology. Okay, and today we will discuss about two types of maps, and these are open maps and continuous maps. Okay, continuous map you have already learned in analysis, so we will discuss the general version. Okay, on for topological space. But let me just start with what is an open map, and then I will tell you the relation between open and continuous map. Okay, so this is the thing. Okay, so suppose we have two topological space x and y and a function if from x cross to y, x, y are topological spaces, and you have some topologies there. Okay, is said to be an open map if image of a if image of any open set under F is also open in Y. Okay, so you take an open set in X, whatever, like this has to be any means is for all open sets. Okay, choose any open set from X and the image has to be open in Y. So what does that mean? That means so that is that if so U belongs to the topology of X, then f of U, this is subset of Y obviously, but this is not only a subset, this is open subset of Y. Okay, this is the meaning of open maps. Maybe I can give an example. So for example, you choose a function from R with usual topology to RL, the lower limit topology. Okay, so you know the meaning of RL. So the open sets are actually union of these open bases, and the basis elements are what? This is so this kind of closed A open B of this form, right? So this map is open. So defined by, say, f of x equal to x, the identity, okay, is an open map. Why this is an open map? You check that whenever you choose and see to check something is open or closed, it is easy to check for the basis element here. Okay, so you know that any open map, open sets of R are nothing but union of the basis elements which are open interval, right? Now you check that any open interval, you find out an open interval A comma B, and the image will be A comma B, because this is identity map. But this open interval A comma B is also open in this, open inside this lower level topology, right? So this map is open map. This is one such example. Okay, now what do you mean by continuous map? So continuous maps is actually kind of the opposite thing. So kind of image of open set is open, it is the opposite thing. Kind of pre-image of open set is open, or pullback of open set is open. Okay, so let me define it for a point, and then I will define it for whole space. Okay, so next definition, the continuous definition. How do I define? So I have a map from x to y, and x and y are topological spaces that is given. So and you have a point, say x belongs to x. Okay, so we say if is continuous at x if for any neighborhood. So neighborhood means open set containing that point, right? Neighborhood of fx in so any neighborhood. So let me write down the name. Say for example V. neighborhood v of fx in y, there exists a neighborhood say u of x such that what happened, such that f of u, this is inside subset of v. Then we say that f is continuous at x. Okay, so whenever you choose a point, you just go to the image of that point f of x and choose any neighborhood v. So there will be one neighborhood such that b actually, if so this is what this means, u actually inside f inverse of v. Okay, so the pre-image of b contains that neighborhood u. Okay, that is the meaning of that. Okay, and if is continuous at x, if is continuous at all points of x. Okay, so what does that mean? So continuity means that for every point you have this property. You take that open neighborhood, or neighborhood of the image. This will be a open set such that f of u is a subset of v. Okay, this is the meaning of continuity at every point. Okay, there is one more meaning, so I'm just going to tell you this first. Okay, so obviously one can ask that okay, so this is the definition. Maybe let me write down definition 1. Okay, definition 1 for continuity. This is also definition 1, like that continuation. Okay, or you can define by other way also. You can say that function is continuous. Okay, definition 2, we can say that f is continuous on x if pre-image of, pullback, whatever you can say, pre-image of every open set is open in x. So if you choose any open set, every open set of y is open in x. So this is, I'm saying that instead of thinking of continuous at every point, you can also think that whenever you have open set in y, the pre-image, that means f inverse y has to be f inverse that set b has to be inside x, has to be open. Okay, in this case also we say that this is function is continuous, and these two definitions are equivalent actually. Okay, so we can say that this definition, this definition 1 and 2 are equivalent. So what does that mean? That means 1 implies 2 and 2 implies 1. Actually, you can also prove that. Okay, so let me just give you a proof. 1 implies 2 and 2 implies 1. So let me just prove that 1 implies 2. So what does that mean? So that means that if it is continuous at every point on the definition under the definition 1, then it is satisfy also definition 2. So what does that mean? So let how to prove this? So let this v belongs to this topology of y. Okay, the open set in y, and you choose a point, say y belongs to v. Suppose you choose a point, say y belongs to v. Okay, and then obviously okay, so okay, so I am going to prove that whenever maybe no, I don't want to choose. I have to prove that other thing. Okay, so no, not this. Y belongs to say b, but yeah, one thing I need to change here. So I choose a point and then and say this f inverse. So I need to check that f inverse v is open, right? So how do I check f inverse v is open here? So you choose a point y belongs to f inverse v. If I prove that this f inverse v is open, union of open sets, then I am done, because union of open set is open, and then it is done, right? No, so you choose a open set, any open set in y, and then f inverse v is this. But what does that mean? That means by definition, the definition 1, there exists a neighborhood of, okay, so what does that mean? So this means, so this implies, so let me write down, this implies f of y is actually element of v, and v is open set which contains this. So by definition 1, there exists a open set in X, okay, such that this y is actually inside, okay, yeah, so open set this such that y is actually inside this open set u, and not only that, and f of u is actually, maybe I can write down this is uy, that is easy to maintain. So this is open set containing y, so let me write down ui, the neighborhood of y, okay, such that f of ui is subset of v, right? Now f of ui is subset of v, what does that mean? That means ui is subset of f inverse of v, right, for this v. Now if I for example, if I now vary all the u, y belongs to f inverse v, then what happen? Thus f inverse v, you can write down this as union of this u of y, and y belongs to f inverse of v, okay. So see here, I choose one element y, and further I find out a open set ui, right? Now similarly, if you vary this element y in f inverse b, so you will have other open sets that contain inside f inverse b. And what does that mean? That means this collection of all such ui that is already inside f inverse b, the union has to be f inverse b, right? And done. So but see, why done? Because this u of y is open set, and you know that arbitrary union of open set is open, so this is element of the topology of X. So what does that mean? That means f inverse v is open, and thus f is that 2 follows, definition 2, okay. This implies definition 2 follows. So 1 implies 2 is proved. Similarly, you can prove 2 implies 1. Okay, so 2 implies 1 means what? If pullback of every open set is open, then what happens? Then for any element of X and neighborhood of f of X, there exists an element, there exists an open set U, which actually the image is contained inside V, right? And that is obvious by definition. Why? So let you choose some element, say X belongs to X, and V be a neighborhood of f of X, okay. So what does that mean? That means V is open in so this means that V belongs to that topology of Y, right? Open set in Y, and thus by definition what happened? That f inverse of V is open, right? But f inverse B, let me write down the name. So U equal f inverse B, so that is inside topology of X. So that means this is open set in X, okay. And now you see that this U is actually, what is U? U actually contains X, right? Because f of U is inside okay, so yeah, X is inside U, but f of X is inside V, so that means X belongs to X as x belongs to U, okay, so x belongs to U, this implies that U is a neighborhood of x such that f of U, which is nothing but V itself, so this is subset of V, right? It's actually V itself, but that means this is also subset of V, right? And this is that definition 1. So definition 1 follows. Okay, so these two definitions are equivalent. To prove something is open, it is better to use definition 2, but to prove something is continuous throughout the space, then it is better to use definition 2. But to prove something is continuous at a point or is not continuous at a point, it is better to use definition 1. Okay, so these are all examples. Okay, now these are all things. Now let me give some examples. Now for example, I have given you example from R to RL, and you remember that this identity map is open map, but you check that this is not a continuous map, not a continuous map. Why is not a continuous map? Yeah, so as I told you, something is not a continuous map. What you can do, you can find out a open set in whose pre-image is not open, right? So so for example, you choose say 0 1, 0 close 0 open 1. It is open in RL, okay, but the pre-image is what? Pre-image is same thing, right? But the pre-image is also close 0 open 1 is not open in R. Pre-image is not open in R. What does that mean? That means that the pullback of this is not open set, so this map is not a continuous map. Okay, on the contrary, if you assume the other map, kind of a map, say for example G from RL to R, such that G of x equal to x, the identity map, this is a continuous map. You check it, continuous map. Why this is a continuous map? Because whatever open set you choose here. Okay, so one more thing I should say, that if you know the basis here, then it is enough to check that pullback of basis element is basis. For example, if of G inverse of any open intervals is nothing but that same, because identity map, and this is also an open in RL. Okay, so this is actually open map. Okay, so what is the important observation here? So whenever you have basis, if you know the basis, because basis is kind of smaller collections, for example, this is, you should remember, so it is given the f from x to y, okay, and you also know that the topology of y is generated by some basis. Okay, then it is enough to check that pre-image of basis element is open or not. Okay, so why? Because whenever you choose any element which is open set in Y, so it will be kind of union of some basis element, right? Some, it doesn't matter, it can be finite, infinite, some basis element. Okay, and you know that under this map, f inverse of B will be nothing but union of f inverse of B alpha, and alpha belongs to lambda. Alpha belongs to lambda. Lambda, not V. Okay, so what does that mean? That means if you know that if inverse B alpha is open, you are done, because you know open set is open. So for basis element, it is enough to check that this F inverse of B alpha that belongs to tau x. This is the thing only you need to prove the function is continuous. Similarly, if you know a subbase of a topology, for example, if something say S is a subbase, maybe SY, let me write down subbase for Y, then it is enough to check that in pre-image of the subbase element is open or not. Why? Because so the basis element B, if B belongs to this basis of Y, then we can return as what? We can return as finite intersection of basis element, right? Some S1 intersection S2, something same Sn, right? And hence F inverse of B is nothing but this F inverse of S1 intersection dot intersection F inverse of Sn, right? If all those F inverse Sns are open set, then final union of open set is open, and hence this is open set inside X. So it is enough to check that whether F inverse of S belongs to tau of X for all S belongs to that subbase or not. Okay, if it is true, then it is enough to check this is true for proving if it's continuous function or not. Okay, so these two are very important observation that will tells you that how to check some function is continuous functions or some functions open functions or not. Okay, for open set also, open function also, if you put something open map, then it is enough to check that so instead of pre-image of open set, you have to go for image of open set. So in that case, if you know the basis element, it is enough to check that image of a basis element is basis open or not. Okay, so now one can ask another important question that, sir, we have already learned the idea of continuity at a point or whatever. So continuity at a point inside real number, right? For example, okay, so classical, remember the classical definition of continuity? Classical definition of continuous functions, okay, continuous maps. Okay, so what does that say? So we say that a function, say for example, let me just first take from R to R, okay, and you have some x naught belongs to R, so we say f is continuous at x naught if for any epsilon positive there exists delta, and that delta is depend on this kind of function of epsilon and that x naught, obviously, such that mod of x minus x naught less than delta implies mod of f of x minus f of x naught less than epsilon, right? This was the classical epsilon delta definition. Now the natural question to ask whether this definition is also kind of coming from whatever definition we just gave, and the answer is yes. Actually, these two definitions are actually equivalent for the usual topology of R. In fact, the way we define it for arbitrary topological space is more general. We can prove it actually. So so what does that mean? That means I'm going to say that the definition we have given for topological space, that implies this definition, this classical epsilon definition. Okay, and how to prove it? So let me give you a proof so that you have understand that it is more general definition, right? So this you can say that definition 1 implies epsilon delta definition of Euclidean topology of R. Okay, Euclidean topology, that definition of continuity under equivalent topology. Okay, so I should mention that topology of R. Okay, why? Because so given epsilon, so I know that given epsilon positive, and find out delta. So how do I find out? So let epsilon positive be given. Okay, and you know that and f is continuous. Okay, so at this point, say x naught. Okay, then by our definition, what you know? So we know that there exists open interval. So I am choosing open interval by this f of x naught minus epsilon to f of x naught plus epsilon. This open interval in equivalent topology. This is my v. Okay, and so this interval actually contains that point, that v of x naught belongs to f of x naught belongs to v, right? So our definition tells us that there exists a open set inside a open neighborhood of x naught such that f of that open set is contained inside v, right? So there exists some open set which is open interval, right? So there exists some AB neighborhood of x naught such that what happened? Such that this f of AB is actually subset of this v. Okay, so what does that mean? That means this AB is actually inside f inverse of this v. Okay, clear? Now because x naught is inside AB, so x naught can be either closer to A or closer to B. So let me just fix delta is minimum of these two quantities, say maybe x naught minus A and B minus x naught. It is in between A and B, right? Whatever is minimum you choose, that is delta, and the moment you choose delta, you find out my new open set, open interval by this u equal to, what is my u? U minus x minus delta to x plus delta, x naught plus delta. Okay, so if I choose this is my open interval u, you see that obviously f of u is sitting inside v, right? And this is also saying that for any such elements which is inside this set, that means whenever mod of x minus x naught is less than delta, that implies f of u is inside v. But what is v? V is this. But this is what? This means f of x minus f of x naught is less than epsilon, right? So this implies the mod of f of x minus f of x naught is actually less than epsilon. Less than epsilon. Clear? So this is the proof that our definition of topology, continuous function under general topology, is actually implies the epsilon definition. But it is also same for usual topology. You can easily check it. For usual topology, it is also same. You can easily prove it. Okay. So now question is that okay. So I hope, yeah. The question is that do we have some equivalent different other forms? The answer is yes. There are many other equivalent forms, and maybe I will tell you something, some equivalent form, and then some property of continuous functions. Okay. So so let me discuss some of the other equivalent forms of continuity. Okay. So some equivalent form of continuity. Okay, clear? So let me just assume that this two topological space. Okay, and obviously I am assuming that that topologies are given tau x, tau y. So I am not writing every time. Okay, and then TFAE that I already discussed before. The following are equivalent. Okay, what are the equivalent? The first thing, number one, if is continuous, I mean continuous on x at every point of x. Okay, continuous. This is first. Number two, for any set A, for whenever you choose any set, okay, for any subset maybe. So A, we have what we have. We have f of a closure is actually sitting inside f of a whole closure. This is true for continuous functions. Okay, clear? And then number three, there are many things, so let me just only discuss three. And number three tells you that whenever you pull back a closed set of y, the pre-image is also closed. So what? So pullback or p-image, whatever, you can write down pre-image also, image of a closed set, pre-closed set, say b of y is closed. So what does that mean? That closed in x. That means what? That means if b complement is inside topology of y, this implies f inverse b is a complement, right? Whole complement is inside topology of x. So that means x minus f inverse b is open set. So f inverse b is a closed set. Okay, this is the meaning. Okay. That is, I should say, that is okay. And this all three are actually equivalent. So either you are saying that pullback open set is open or pullback closed is closed, doesn't matter, or image of a closure of a set is sitting inside the closure of image of the set. Okay, these are all equivalent. Okay, so now let me prove one by one, and then you will have more definition. Okay, then you can actually use any definition to prove continuity. Whichever is easier for you, you can prove that. Okay, now let me prove 1 implies 2, 2 implies 3, and 3 implies 1. Then I am done. Now 1 implies 2. Let me first prove. What does that mean? Then I am assuming that it is open set, a continuous function, and that means pullback of open set is open. And I need to prove that image of closure of any set is actually inside closure of the image of that set. Okay, so let me assume that. So let f is continuous, which is 1 is given. Okay, and I need to prove that, and obviously it start with a set subset of x, say a subset of x. Okay, so what I need to prove? I need to prove that for any okay, so let we choose any point, say x belongs to a closure, and I need to prove that so this means what? This means if f belongs to a closure, that means this means that f of x is element of f of a closure, right? This is obvious. Yeah, so what I need to prove? I need to prove that f of x actually belongs to f of a whole closure, right? So this is I know already, but what does that mean, f of a closure? Okay, oh no, sorry, we need to show actually no, let me write down first what I need to show properly, then you will have so we need to show that f of x, that means f of this has to be inside f of a whole closure. This is I need to show, right? This is I need to show. So if this is I need to show, what I need to show, see one thing is clear, that okay, so 1 minute. So this is continuous map is given, so that means continuous at a point. So it is continuous at a point x, means if we have open neighborhood of fx, so let v be a neighborhood of f of x, and whenever you have a neighborhood of x, then what happen? Then you have you open set, then and u be a neighborhood of x such that f of u is sitting inside v. This is given to me, right? Because this is the function is continuous, it is given. So what does that mean? That means u is actually sitting inside f inverse of v. Is that okay? Clear? But rather I can obviously prove other way also. I think this is open set that I just choose my u equal to f inverse b. That is enough actually. In fact, I can choose my u equal to f inverse b because open is given, so f inverse v is also open. Okay, because I am assuming the continuous at every point. Okay, so f inverse b is also open, so I can either choose this or that, but doesn't matter. So this either you choose u is open set of f inverse b, or you can choose u equal to full f inverse b, right? So in any case, u is a neighborhood of v. X, okay, so x belongs to u. This is, you know, right? And also you know that x belongs to a closure. What does that mean? X is element of the closure of a, and you know that by definition of closure of a, every open neighborhood or open set of x that intersects a intersect means the intersection is trivial. This implies what? This implies u intersection a is always non-trivial, okay, because a is x belongs to a closure, right? So what does that mean? So yeah, so this means that you can find out some elements. So y belongs to u intersection a, and this implies f of y is a element of f of u which is inside v, okay. And also not only that, f of y belongs to a means f of y also belongs to f of, right, also this is also element of f of a. Clear? Because y belongs to u, so f of y belongs to f of u, but f of u is sitting inside v. This is one. Also y belongs to a, so that means f of y belongs to f of a. So y is the element of v intersection f of a. So what does that mean? That means that whenever you have every neighborhood, this f of y, whenever you choose any neighborhood of f of y, so this neighborhood actually intersects f of a. Okay, is that clear? So v intersects f of a in these points. So what does that mean? So v is a neighborhood of fx. See, look at this. V is arbitrary neighborhood of fx. Yeah, v is arbitrary neighborhood of fx. Clear this line? So whenever you choose a neighborhood of fx, you have an element which intersects f of a. So this implies that f of x is actually inside the closure of this. Yeah, this is the meaning, and this is obviously we need to prove, because originally f of x was arbitrary point. So f of x belongs to this means what? This means that f of a inverse is a subset of f of a whole inverse. Okay, this is the meaning of that. So I choose an element from x from a closure, so f of x will be f of a closure. Now I also prove that f of x belongs to f of a whole closure, so that means f of a closure is a subset of f of a whole closure. Okay, so this is number 2 that proves. Now let me give 2 implies 1. Okay, now 2 implies 1, 2 implies 3. So now for 2 implies 3, what do you need to prove? 2 implies 3. So 2 implies 3 means I am assuming that for any set A, f of a closure is subset of f of a whole closure. Okay, now I need to prove that pre-image of a closed set is closed. Okay, so so let me start with a closed set first. So let B be a closed set in Y. If B be a closed set in Y, and then you write down, say, pre-image, maybe say A, if inverse of B. This is pre-image of that. So I need to prove that A is closed set. So what we will prove? So you will show that A closure equal to A. That means A is closed, right? That we already discussed in last class. That a closed set is some closure is closed. That means the closure is itself, right? But one part is obvious. So we also know that so A subset of A closure always, right? Is always. So so what we need to show? We need to show, so thus we will show that, what we will show? We will show that A closure is a subset of A. That we need to show only. So what does that mean? That means every element of A closure is also element of A. This is the only thing we need to show. Okay. So let me start with an element. So let me start with an element of A closure. So so let X belongs to A closure. Okay. Now if X belongs to A closure, then that means that f of X belongs to f of A closure, right? But from our previous number 2 implies 3, right? So 2, what is 2 is telling? 2 is telling that whenever whatever is A, f of A closure will be always subset of f of A whole closure. So what does that mean? That means your X is an element of f of A closure, but f of A closure is a subset of f of A whole closure, right? Clear? This is that okay? Okay, so this is equation number 1. On the other way, you also know that whenever if A is, say, f inverse of B, then you can take image of A under F. That will be nothing but f of f inverse of B, and this is a subset of B itself, right? This is also you know, right? Now number 2, this is number 2. Now if we use number 1, number 2, then what does that mean? That means the X is element of f of A whole closure, and by f of A whole closure is subset of B closure. So that means f of A, X belongs to f of A whole closure, which is subset of B closure, but B is closed set, right? I started with the closed set B, right? B is a closed set in Y. So what does that mean? That means B closure equal to B. But what does that mean? B closure equal to B. That means X is an element of B. Clear? Now if X is an element of B, so what does that mean? Oh sorry, not X, 1 minute. So I think f of X, yeah, this should be f of X, not X, yeah. F of X is an element of B, because X is element of A closure, right? So f of X will be f of X is this is f of X, not X. F of X belongs to f of A closure, and so this is subset of f of A whole closure, and thus f of X belongs to f of A closure, which is subset of B closure, but B is a closed set, so B closure equal to B. So f of X belongs to B. Now f of X belongs to B, what does that mean? That means every element of, for every element of A closure, it's element of B, right? F of X belongs to B means, okay, so this means X belongs to f inverse of B, right? But what is f inverse of B? F inverse of B equal to A. You see, f inverse B equal to A, right? So X belongs to A. So this implies X belongs to A, and thus A closure is a subset of A, and hence A equal to A closure. So A is closed. So A is closed. So what does that mean? That means f inverse, which is nothing but f inverse of B, right? So I just proved that the image of a closed set is closed, right? Okay, so okay, and now finally we need to just prove that 3 implies 1, and then I am done. So now for 3 implies 1, what I need to prove? So I know that pullback of closed set is closed. I need to prove that pullback of open set is open. And this is simple. So you just take, let V belongs to open set of Y. So maybe say tau of Y, and obviously that means Y minus V is a open set, Y must be is a closed set. So let me write down this is B is a closed set in Y. Okay, so if something is closed set in Y, then what you can do, then you can write down what about the pre-image of that B. Okay, so let me write down pre-image of B, and this is obviously nothing but F inverse of Y minus F inverse of V. Okay, it's a set theory. Okay, F inverse of B, not closer. Okay, this is F inverse of V. Okay, now F inverse of Y is what? F inverse of Y is nothing but X, and F inverse of V, right? But you know that what do you know? You know that B is a closed set, and by assumption number 3, F inverse B is closed set, right? And hence you can write down that F inverse of V is nothing but X minus F inverse of B, which is a closed set, and F inverse B is nothing but complement of a closed set, and hence F inverse B is open. So this means this is element of the topology of X. Okay, this is the proof. So you start with the element which is open in Y. Now you prove the F inverse B is open in X, and this shows that inverse image of every open set is open, and hence that our first definition, like whatever I assume, this is true. Okay, so this completes the proof that saying that image of closed is closed and pre-image of open is open, they are equivalent. And in sometimes in real situation you may need to use the first theorem, sometimes you may need to use the second theorem. Okay, maybe I will stop here, and there are many some properties that maybe we will discuss in next day, next lectures. Okay, so today I am going to stop my lecture now.